talking about chapter 14 in our textbook. And in chapter 14, we are only going to cover sections 14.1 and 14.2. So 14.3, which is an optional section, which talks about variable systems of particles, we're not going to discuss in this class. One thing I wanted to point out on your Moodle page, one of your classmates had pointed out to me that on the lectures, when they're downloaded or uploaded to YouTube, that sometimes the PowerPoints that I'm speaking about do not come out very clearly. So I have posted the PowerPoints separately on the Moodle page for you. That will just allow you to print them out or to view them while you're viewing the lecture and just give you a little bit more visual clarity with the material. So the chapter 14 PowerPoints, I've posted the entire set, which there are 26 slides, and we're only going to cover about the first 20 because at slide number 21, we start talking about variable systems of particles, which is actually that optional section 4.3. So if you're going through the PowerPoints and you feel like I've lopped off the last 6 or 7 PowerPoints, that is correct. So you don't have to learn them or be fearful going into the test that material is going to be covered, because it won't. All right. So in this chapter, today we're going to cover about 10 of the slides. We're going to, over the entire chapter, we're going to cover slides 1 through 20. And I've never really done this before, but I'm making this information available to you because since I'm posting the PowerPoints, when I just put the PowerPoints up while I'm talking, obviously I don't put up the ones that I'm not talking about, so it's not an issue. But we'll do slides 1 through 20 for the entire chapter. We omit section 14.3, so we omit slides 21 through the end, all right? Just so that we're all kind of on the same page. All right, so coming back over and taking a look at the PowerPoints. When we talk about systems of particles, what we're discussing is situations where there are more than one discrete mass center. So, for example, once again, getting back to the idea of pool balls on a table, if you have one ball that hits one ball and then that ball hits another ball or hits the side of the table and then bounces back, you're talking about something that you really have, you have a center of mass that is not located on necessarily one of those discrete points, and also it can be moving. And the center of mass can be moving in a different manner than the balls themselves, because some of the balls may be sitting still, some of them may be bouncing around on each other. And so these are some of the considerations that we will take into account. Now, you may know at this point in your academic career that anytime you talk about creating a summation, you really talk, if it's a continuous function, you can talk about it as an integral. And so we've done a lot of things as integrals to this point because we have a shape where the mass is distributed about some center. And that becomes a little more difficult for a system of particles where the particles are discrete. So we tend to rely back on a summation, on a true summation, rather than an integral. But the principles are still the same. The same things are conserved, the same things are not conserved, the same principles apply. And once again, almost everything comes out of Newton's second law. So he invented that, or he came up with that back in the 1700s, and here we are 250 years later, more or less, still working with it. So the first slide, we talk about applications of Newton's law and this idea of effective forces. Now, when we talk about effective forces, it's defined as the product of a mass and an acceleration. So what we're really talking about is, if we look at Newton's second law, F, or summation of F, equals ma, we are not really talking about what's going on outside, we're talking about what sometimes is referred to as the inertia vector. So we have to break down a little bit differently what happens inside of a system of particles, because if we have a single particle, it's quite easy to see what's inside and outside. But we just have to make this distinction and decide what's going on effective inside of the system and what's going on outside of the system. And the statement that it says it will be shown that the system of external forces acting on a system of particles is equivalent with the system of effective forces. That just means what's going on outside is essentially mathematically equal. Equivalent just means equivalent to. It's not fully equal. I'm not trying to oversimplify that, but it's, in terms of mathematically, it's equal to what's going on inside of the system. And all this really depends on that idea of the mass center. Okay, so there we go. So if we take a look at this first one, what we're saying is, if you look at the subscripts, I want to be really clear about this. It says the vector f sub I plus the summation from j equals 1 to n of the vectors ij is equal to mass mi times the acceleration of I. Okay. Now, when we talk about I and j, we're not talking about directions here, and I really want to be clear about that because I find this to be potentially very confusing. We're not talking about x, y, and z unit vectors, or unit vectors in those directions. The vector fi refers to external forces. The vector f, and they put it as a small vector, ij refers to internal forces, and mi, refers to the effective force. And once in a while, if you had a single vector or a single particle, you could refer to the effective force as being the inertia vector. So it's what it takes, what has to be overcome in order to move this. So this equation looks a little odd, but we're basically talking about the external forces and the internal forces acting on the mass center of the system. Okay, the second equation, we are also talking about moments. So we have the moments caused by external forces on the mass center, or on, in this case, they're just looking at a particular particle. And they're saying, well, there's one particle that's being acted on by these other particles, but they're all in the system. So then this, of course, would be the internal forces, and their moments is equal to R crossed with MA, which is, for those of you that have been in statics, is quite similar to the moment of inertia of the object. So we talk about the system of external and internal forces is equivalent to the effective forces, the effective force on a particle, and the system of external and internal forces acting on the entire system is equivalent to the system of effective forces. Okay. So internal, external, inertia. Those are the three ideas that we're talking about. All right, so if you sum up all these elements, we need to get to something that is somewhat useful. And here we just have a system that consists of two particles, and here we have a system that consists of three particles, and it depends on whether we're talking about them being internal or external. But we sum everything up, both in terms of forces and inertia, and moments of inertia. And we come out with this idea that since the internal forces occur in equal and opposite collinear pairs, the resultant force and couple are due to the internal forces, and those are equal to 0. All right, so we just eliminated a whole big bunch of nonsense by running through the vector math, and then we come up with the F sub I equals MIAI. So once again, if we go back and take a look at the previous slide, we see that we're talking about external forces when we subscript with the I. So basically we're saying the summation of the external forces is equal to the mass times the acceleration, and the acceleration here is going to be of the particle that is in question or the center of mass of a system of particles. So in other words, we can look at this as being each particle individually, and the same thing here. So we're trying to reduce this because right now if you had 10,000 particles, this would be a ridiculous amount of work. Now with MATLAB, you could probably do it relatively quickly, but it's not exactly something that most people are itching to do a 10,000 by 10,000, evaluate an array of that sort. All right, so we can then talk not only about F equals ma in terms of mass and inertia vectors, we can also talk about it in terms of linear momentum. And for systems of particles, we find that in general, we can say that the summation of forces is equal to, you see there's a little dot, which is another good reason that you asked me to post the PowerPoints, because you're probably not going to be able to see this unless you pull up the PowerPoint yourself. But it's basically saying that the summation of forces is equal to the rate of change of linear momentum. And once again, this all extends from Newton's second law, because force is equal to mass times acceleration. Acceleration is dv dt. So if mv is L, m dv dt is the rate of change of linear momentum, assuming that mass doesn't change. But if we put the mass inside of the derivative function, then it's exactly the same. All right, then we get into the idea of linear momentum, and we can say then that the summation of the moments about some point is going to equal the rate of change of angular momentum if we're discussing the same point. And the big thing that we're trying to get at here is defining that center of mass, because the point where all this makes the most sense is if we take it about the center of mass of that system of particles. All right. So the center of mass is defined by this position. And I like to think about, there are three different thoughts that you may have heard in statics or in physics. There's a center of mass, a center of gravity, and a centroid. All right? Now, a centroid is really a geometric point. So if there's no distribution of mass, and if you're in a standard gravitational field, all three of those things will coincide. Okay? But what we're really talking about, because we're back to Newton's second law where force is equal to mass times acceleration, we're talking specifically about the center of mass. Now, a center, that means a point where the moments created by all those discrete mass points equal zero. The way I like to think about it in practical terms is it's a little bit easier for me to think about it with a center of gravity, but considering that there are many cases where those coincide, that's easy enough to do. It's a balance point. So if you have something that is irregularly shaped and irregular distribution of mass, there's going to be some point at which that will balance. And that point is the center of mass. I didn't pull this up today, but in one of the, oh gosh, it's an old Nicolas Cage movie, one of the National Treasures, where they're in South Dakota, and they're trying to, they have a table, and they're having to jump onto it and put people at different points to make themselves not fall off. That's an awesome center of mass problem. I don't think the physics is 100% accurate, but it's a good idea of what you're trying to do when you're finding a center of mass. And what an easier problem is like kids on a teeter-totter. Do you guys ever use teeter-totters anymore? See, okay. So I didn't know if it was kinder and gentler now. We couldn't have teeter-totters. We used to slay each other on those things. But anyway, it's like you have a heavier kid and a lighter kid, and kid over here just keeps his little brother up in the air forever. You know, you can't get down, right? So the way that little kid can do it is to scoot farther back to create the center of mass that coincides with a pivot, or there's little cups that you can slide differently to make one side shorter and one side longer, or you can enlist the help of another little kid to get the big kid up in the air and then not let him down. So all of those things are talking about center of mass. And some shapes are, if you have enough symmetry, finding the center of mass is easy. If you don't have a lot of symmetry, it can be a little bit more difficult. But this is basically the idea that the center of mass of a system of particles is defined by this position vector r sub g, which satisfies this equation. And so we can take that idea of mass center and we can differentiate it and equate it back to the summation of forces. So this actually comes out to be what we discovered on the earlier slides, where forces is equal to the rate of change of linear momentum, and forces is equal to rate of change of linear momentum. But now we also know that it's equal to the mass times the acceleration of that center of gravity, okay, which is sort of where sanity intersects this concept. Otherwise, if you don't think about center of mass, you can still do it, and sometimes you will work problems without doing the center of mass, but you have all of those different internal forces and equipolant systems and everything else. So if you just put everything back to the center of mass, everything behaves more like a single distributed load or distributed particle. All right, and this just kind of does the same thing, talking about the angular momentum of about the center of mass. So we have the angular momentum, and if you go through the math, turns out to be the summation of moments about the center of mass. So if you remember, in every single case, a moment is r cross f, or r cross ma. And so if you have an r cross f, the r is always then going to extend from the point that is the center of mass to the application of the force. So we always have that same point, g, in this case, which they're saying is the center of mass. Okay, so we start talking about the acceleration of the center of mass, the velocity of the center of mass, and any type of movement of the center of mass, as well as the fact that if the system is moving, if the particles are all moving in concordance with each other, the center of mass will move in a more logical fashion. But the logic of a center of mass movement, if the particles are moving in different directions, you really have to do that through the math. You just really can't. I shouldn't say that. You guys are all bright, but visualizing that is bizarre. So I would recommend that you fall back on the math to do that. All right. So then once again, we're just, what all of these slides is just telling you is find the center of mass, make everything work about the center of mass. Okay? And then this is just a statement of the conservation of momentum, which kind of finishes off this topic, where if we have no external forces acting on a system, then the linear momentum and the angular momentum about the fixed point O are conserved. This goes back to that idea of angular momentum is not generally conserved, right? Angular momentum, first of all, has to be defined about a point, and angular momentum is only conserved if it's being acted upon by a central force. So this is sort of the equivalent of that statement for a system of particles. And then in some applications, such as problem involving central forces, we have that as a given. And so then the concept of conservation of momentum also applies to the analysis of the mass center. So if we find that mass center, we are golden. So if we take everything about the mass center and some about the mass center, then we have sort of a concordance of a way to view everything. All right? So a lot of that is not the only way that you can look at it. It's just a way you can look at it that will help you minimize the dross that's going on in other ways. All right. So do you guys have any questions at this point? No questions? All right. Well, I wanted to come over to the document camera, and I wanted to take a look at 4.1 so that we could start to talk, or 14.1, I did write it down correctly, problem 14.1, so that we could discuss some of the ideas of how we're going to approach these types of problems. And sometimes the problems are not really all that complicated if you just think about, you can think about them more or less discretely is the best way I could describe it. All right, so if we take a look at problem 14.1, we have a 30-gram bullet. Okay, and it's being fired with some velocity. It's strictly horizontal, and that is 450 meters per second, and becomes embedded in block B. So block B is set to slide on a cart that looks like this. Okay, which has a mass of 3 kilograms. All right. After the impact, block B slides on the 30-kilogram carrier, which that's pretty heavy, but that's okay, until it impacts the end of the carrier. So we actually have 2 impacts going on here, don't we? Knowing that the impact between B and C is perfectly elastic, is that E equals 1, right? Knowing that the impact between B and C is perfectly plastic, there we go, and the coefficient of kinetic friction between B and C is 0.2. Determine the velocity of the bullet and B, because of course they're going to be combined at that point, aren't they? Bullet and block B, okay, after the impact, and the final velocity of the carrier. All right, so we really have 2 different steps here, don't we? The first thing we have is the momentum of the bullet being imparted into the block, all right? And it's going to embed itself in the block. And initially, B is going to start sliding. There's going to be a coefficient of kinetic friction, so B will be opposed by friction. And then when it hits the wall on block C, the whole thing is going to move forward, right? And so when the bullet embeds itself in block B, the first thing is they're going to move ahead with, oops, I've got my thing over the microphone here, sorry. It's going to embed itself. We're going to have a velocity of the 2 combined. And so let's talk about that first of all. All right, so let's pretend like the cart doesn't exist. We have block B that looks like this, and we have the velocity of the bullet. And those 2 things together are going to be the block plus the bullet. Okay, so this is what our system looks like. Now, the first thing is, if we think about this in terms of linear momentum, everything's in the x direction, so that's relatively easy. We could say that the mass, I'm going to call this, did they call this? I'm going to call this A, just because otherwise block and bullet just get confusing to me. So if this is B, let's just call this A. The mass of B times the initial velocity of B plus the mass of A times the initial velocity of A is equal to the combined masses times the final velocity of the 2 added together, right? And to use the nomenclature from the last section, we would call that V prime. Well, the block is not initially moving. So we can then simplify this equation to just say the mass of A times the initial velocity of A is going to equal the combined mass of B plus the mass of A times the velocity after the impact. All right, so if we want to solve for the velocity of the bullet plus the velocity of B, I'm calling that V prime. So I can then say the mass of A times velocity of A over the mass of B plus the mass of A is equal to V prime. And the only thing I really need to do here, the mass of this is 30 grams, which I should probably consider writing that as kilograms, just so that I don't have a difference in my units. And everything else is in kilograms. It would be equally accurate to put everything in grams, but since the carrier and the block are both in kilograms, let's just simplify it as much as possible. All right, so my mass of A is 30 times 10 to the minus third kilograms. And my initial velocity of the bullet is 450 meters per second. Now, you could argue that this should be negative, but everything is going to move in that way. So I'm just going to call it positive. The other thing is that we start talking about the friction between B and the carrier. The friction is going to oppose. So if I make the velocity negative, that's going to have to make my friction positive, which just looks weird. Now, you could still do it, but it just looks a little bit better to me to do it that way. All right, so then my masses then are going to be 3 plus 3 times 10 to the minus third kilograms, right? Equals whatever that number turns out to be. Okay, so my kilograms will cancel out, and I'm left with meters per second, which is a great unit for velocity. So if I take, gosh, that's just a tiny little number, isn't it? 30 divided by 1,000. That's actually 0.03 kilograms times 450. And then I divide that by the sum of 3 and 0.03 kilograms on the bottom. Turns out that my velocity is 4.455. That's too many decimals, but or too many significant figures, but I'm going to leave it that way. Meters per second. And that will be, of course, in the same direction as the bullet. It would not make sense for anything to turn around. But there's 4.455 meters per second. You've slowed it down considerably by a factor of 100 from the initial velocity, which makes sense. That's what happens when bullets, for example, are fired into heavy objects, into trees and so forth, that they kind of they quit or almost quit moving. But what happens in this case is now we have this block B with the embedded bullet in it, and it's going to start to slide toward the end of the cart. So this is part 1 that we've done, and this is part 2. All right, now the first thing is that we're going to have a frictional force opposing this in the amount of mu k times the normal force, because everything's perpendicular. All right, and so what we can see here is that we can think about at first the initial momentum, which is, let's just do linear momentum of B plus A, plus the initial momentum of the cart at C, which is, of course, 0. Oh, plus that impulsive force. Sorry, because we've got the friction going on that we need to take into account, is going to equal the final linear momentum of B plus A plus C. Okay, so in other words, really what's going to happen is when this starts moving, it's going to drain off some of the momentum or some of the energy, even though we're not talking about energy, but basically it's going to drain off some of the energy based on that idea. All right? All right. So we can think of this then as being the mass of b plus a times that intermediate velocity, which I called v prime, which I may actually need a better term for at this point, but I'm not going to mess with it. Let's just do this. Then this would be the mass of a plus b plus c times, oh, let's just say I need to get into account that final velocity. Let's just do this. Let's just do momentum balance right now, is equal to this times the very final velocity. Okay, now the way I have this, I've not really changed my superscripting on this, so we have to keep that into account as well. But basically what we're looking for is the final velocity, but we need to think about what's going to happen in terms of that friction. Well, if we think about particles A, B, and C are all going to have that same velocity, which I'm just calling v sub f, after we have this hit. We can think about the conservation of linear momentum and what happens to this impulsive force. Well, the answer is that this becomes an internal force. Okay? And so, do we really have to take it into consideration? If we go back to our original equation, we can avoid using that, even though we could calculate that, but then we'd have to come up with a period of time, which also gives us another instance of pause. So what we can think of at that point is what's going on in an intermediate sense. This isn't really V final. That's what's kind of making me crazy here. Let's think about it. Let's think about it this way. If we talk about that V final, we could say that that's equal to m of b plus a times some kind of an intermediate velocity divided by the mass of a plus b plus c. Okay. But that it's also going to equal to the mass of a times the initial velocity of a divided by all three of those velocities. Because if we think about this from start to finish, in other words, if we eliminate the middleman, we can say that all of the momentum is imparted by this bullet, which is just the 450 times the little bitty weight, right? And that is going to equal the mass of all three of those objects times the final velocity. So these two are equipolant systems, aren't they? Okay, well, in terms of our computation, we can just think about this and say that's 30 times 10 to the minus third kilograms times that initial velocity, which is 450 meters per second, divided by the mass sum of all three. 30 times 10 to the minus third, plus 3 for the block, plus 30 for the cart. And we're going to find that that velocity is going to be slowed way down once again. But if we do that, we can say 0.03 times 450 divided by the sum of 0.03 plus 3 plus 30, and that number is 0.4087, and that's going to be in meters per second. It's a little bit too much in terms of significant figures, So I would say 0.41 meters per second. And since I defined that direction to the left, we can just leave it like that. Now, the interesting part about that is by doing that, we can leave out that friction term, can't we? We know that something's going on with that friction, but if we start by looking at the beginning and the end, instead of looking at that intermediate step, we can actually avoid having to talk about the impulse that comes from the impulsive force of friction. If we did it in that intermediate step, we would also have to, if we do it the way that we would have done it before as a two-step problem, we would have to determine some way to find a time over which that package slid. And you could do that because they give you that it's 0.5 meters, but you'd have to assume, is it a constant acceleration, and some other things as well. So it actually simplifies your life by doing it this way. All right, you guys have any questions about that? All right, then, let's just go ahead then and call that a day. Let me come back over here to the podium PC. So this is kind of your summary sheet for what we've talked about so far. And I will just assign you like 2 homework problems. Since I did 14.1, I'll probably assign either 14.2 or 14.3, and then one other problem. Maybe I'll do something that's really highly vectorized, like 14.11, so that you can really get into the equations with that. We'll only have 2 more problems, and then we'll come back and discuss the rest of this on Wednesday. So
the problem change if it wasn't embedded inside the block?
Yeah, it would. But what if it embedded inside of if it flew through the block and embedded in the cart, then it's kind of the same thing. You lose kinetic energy, though. I mean, that's every time that you do something like that, you're losing kinetic energy. But the momentum will still be conserved. So, excellent question. Yeah. All right, thanks, guys. I'll post this lecture. I've got the PowerPoints up. I'll post 2 homework problems, and we'll see you Wednesday.